On June 22nd, 2026, NASA put its name on a finding that had been building quietly for almost a full year. A team of its own scientists, led by astrochemist Martin Cordner at Goddard Space Flight Center, confirmed in the pages of the journal Nature that the interstellar comet 3IATLAS is carrying chemistry unlike anything ever measured in a comet native to our own solar system. Not a rumor, not a leaked internal memo or an unverified tip. A peer-reviewed paper backed by NASA's own instrument describing an object that appears to predate the Sun itself. It's the kind of finding that would ordinarily take years to fully digest, except that this particular object doesn't have years to give anyone. It's already retreating, fading, and heading permanently out of reach, which is exactly why NASA moved as fast as it did to confirm and publish what it found, pushing the paper through review on an accelerated timeline that reflected the genuine urgency of the situation. This is the story of how that confirmation came together, piece by piece, across nearly a full year of observation, and why the specific detail buried inside it, a ratio of heavy hydrogen to ordinary hydrogen, turned out to be one of the most genuinely significant things James Webb has measured since it opened its eyes on the universe in 2022. To understand why NASA's confirmation matters, you first need the object itself. 3IATLAS was discovered on July 1st, 2025, by the NASA-funded ATLAS survey telescope in Rio Hurtado, Chile, a network built primarily to watch for asteroids that might threaten Earth rather than to hunt for exotic interstellar visitors. Astronomers traced its motion backward through archival images and found it had actually been sitting there, unnoticed, since May 7th, more than 50 full days before anyone flagged it as anything unusual. Once enough data points came in, the shape of its path left absolutely no ambiguity. This wasn't an object orbiting the Sun, it was passing through, on a hyperbolic trajectory open at both ends, arriving from interstellar space and destined to leave it again forever. The mathematical signature that immediately separates a solar system native from a genuine outside visitor. That designation, 3I, means it is only the third confirmed interstellar object in recorded human history, after Oumuamua swept through in 2017 and Borisov followed in 2019, a rate of roughly one confirmed discovery every 3 to 4 years. Purely limited by how sensitive our survey telescopes have been up to this point, a limitation the field has been actively working to overcome ever since Oumuamua's brief, tantalizing appearance first revealed how much humanity had likely been missing. It was moving at roughly 130,000 miles per hour when discovered, a speed that only kept increasing as the Sun's gravity pulled it steadily inward, and it never posed the faintest threat to Earth or any other planet. NASA's own public guidance was clear on that point from day one, and remained unchanged throughout the entire observing campaign. What made 3IATLAS different from the two interstellar visitors before it was, first and simplest, its size. Because the solid nucleus is too small and too shrouded in dust to photograph directly, even with the sharpest telescopes available, astronomers have to work backward from brightness and reflectivity to estimate it, using the same underlying physics that lets a photographer estimate a distant object's size once its distance and how much light it reflects are both known. NASA's Hubble Space Telescope, using a team led by UCLA astronomer David Jewett, captured the first true photograph of the object on July the 21st, 2025, when the comet was about 277 million miles from Earth, and used that image to narrow the nucleus down to somewhere between roughly 1,000 feet and 5 miles across. It's a wide range, reflecting genuine uncertainty in how reflective the comet's surface actually is, but it was considerably tighter than anything ground-based telescopes had managed on their own up to that point. A real narrowing of the uncertainty rather than a cosmetic improvement. Even at the conservative end of that range, 3IATLAS dwarfs Oumuamua, estimated at under 400 meters and famous for its strange, elongated shape, comfortably outsizes Borisov's roughly 700-meter core, the second interstellar object, which behaved much more like a conventional comet from the moment it was found, right down to its visible tail and coma. It arrived not as a faint, easily missed streak, but as the largest, brightest, best documented interstellar object humanity has ever had the chance to study. And that size bought scientists something precious, enough time and enough signal for essentially every major telescope on and off the planet to take a real, sustained look before it faded from view, rather than the rushed closing window glimpses Oumuamua and Borisov each afforded researchers in their own, much shorter observing campaigns. James Webb's first real engagement with the object came on August 6, 2025, when using its near-infrared spectrograph, known as NER-SPEC, while the comet was still more than 3 times farther from the Sun than Earth is. NER-SPEC doesn't produce a picture in the conventional sense. It splits incoming light into its component wavelengths, the same basic principle as a prism splitting sunlight into a rainbow, and measures precisely how bright the light is at each one, because every molecule absorbs and emits light at its own distinctive set of wavelengths, a kind of chemical barcode unique to each substance. That spectrum functions as a chemical fingerprint. letting scientists identify exactly what a distant object is made of, without ever touching it or needing to bring a single physical sample back to a laboratory. What Webb found surprised the team analyzing it. Ordinary comets are water ice bodies first and foremost, and as they warm near the sun, water vapor typically dominates the surrounding coma. The cloud of gas and dust an active comet sheds as it heats up. 3IATLAS's coma wasn't dominated by water at all. Webb measured one of the highest carbon dioxide to water ratios ever recorded in any comet, interstellar or solar system alike, alongside carbon monoxide, water ice, and a faint trace of a sulfur-bearing compound. Researchers offered a genuinely elegant natural explanation. If the comet originally formed farther out from its home star, in the region of a protoplanetary disk cold enough to preserve carbon dioxide ice, but beyond where water ice would already have been driven off by starlight, it would have locked in exactly this kind of carbon dioxide-heavy composition at birth, a chemical signature stamped into the object before it was ever ejected from its original solar system, and preserved essentially unchanged across the billions of years it subsequently spent drifting through the cold of interstellar space, untouched by any star, until it finally crossed paths with our own. That first result landed in the middle of a genuine controversy that deserves to be told honestly, because it shaped how carefully every subsequent claim about this object got scrutinized by the wider astronomical community. 2 weeks before Webb's observation on July 16th, Harvard astrophysicist Avi Loeb and a small team of collaborators posted an unreviewed preprint exploring, as they described it themselves, a pedagogical thought experiment. Could 3IATLAS's size, its retrograde orbit tilted close to the plane of the planets, and small deviations in its trajectory from pure gravitational motion be consistent with deliberately controlled, potentially hostile technology rather than a natural comet? The paper was framed as a set of testable predictions rather than a confident conclusion, explicitly inviting other researchers to check the claims against incoming data rather than presenting itself as a settled finding. But headlines compressed it fast into something closer to an imminent alien threat, stripping out nearly all of that original hedging along the way. A familiar pattern for how nuanced preprints travel once they leave the hands of the scientists who wrote them. The pushback from working astronomers was immediate and specific, arriving within days rather than weeks of the original preprints posting online. University of Oxford's Chris Lintott told Live Science the suggestion amounted to nonsense and was an insult to the genuine research already well underway. University of Hawaii planetary astronomer Karen Meach called the framing irresponsible, pointing out that 3IATLAS was behaving exactly like an ordinary comet in every measurable respect, down to the smallest details of its outgassing, rotation, and overall brightness curve. University of Regina's Samantha Lawler, while defending scientists' general obligation to test unconventional ideas rather than dismiss them outright, said this particular paper pushed that principle past a reasonable limit, given how thin the actual evidence base genuinely was. Loeb himself has never claimed certainty, describing the hypothesis instead as worth exploring on its own analytical merits, regardless of how it ultimately turns out, a considerably more cautious framing than the one that ended up driving most of the coverage across news outlets and social media alike. That disagreement, playing out entirely in public between named credentialed scientists, is the real texture of how the story actually unfolded. Not a cover-up in either direction, just science working out loud in front of an audience, exactly the way it's supposed to when a genuinely unconventional idea gets floated and then tested against real evidence, rather than simply argued about in the abstract. A second, more technical round of the same argument surfaced that fall. As 3IATLAS swung through its closest approach to the Sun on October 29, 2025, passing just inside the orbit of Mars, its trajectory showed a small non-gravitational acceleration, the kind of subtle deviation from pure gravity that essentially every active comet exhibits because uneven outgassing acts like a weak, irregular thruster as ice sublimates unevenly across a rotating surface. Loeb flagged the acceleration as unusually large and folded it into a broader, continually updated list of anomalies he kept building throughout the campaign, a list that eventually grew to include the comet's unusually close pass near Jupiter's Hill radius, the outer boundary of Jupiter's dominant gravitational influence during a flyby in March 2026, and an earlier ground-based spectral reading showing an unusual ratio of nickel to iron in the comet's outgassing, without the cyanide signature that would normally accompany it in a typical comet. Researcher Thomas Marshall Eubanks and colleagues, publishing their own analysis and research notes of the American Astronomical Society, reran the acceleration numbers and found them entirely consistent with normal cometary outgassing, nothing that required an exotic explanation. Other astronomers pointed out that the nickel-to-iron imbalance falls within the natural range already documented across the broader population of known comets, once measurement uncertainty at that extreme distance from the Sun is properly accounted for, and that the Jupiter flyby distance, while a genuinely interesting coincidence worth noting, was effectively locked in by the comet's arrival speed and angle long before it ever reached the outer solar system, rather than the result of any active steering on the object's part. Around the same period, radio astronomers with the CT Institute and Breakthrough Listen pointed the Allen telescope array at the object and sifted through tens of millions of individual radio detections, finding nothing resembling an artificial transmitter at any power level their instruments could detect, effectively ruling out an active broadcast from the object during its entire approach and departure. Every serious test anyone actually ran came back pointing in the same direction. Natural comet, unusually large, unusually far-traveled, chemically distinct, but a comet, a conclusion that held up across every independent group and every independent instrument that took a look. It was against that backdrop, an object already famous, already argued over, already extensively measured by nearly every major instrument capable of reaching it, that Webb went back for a second, deeper look, in December 2025, and this is where the story's most visually striking results showed up. Between Webb's first NIR spec session and its return with MIRI, the comet made its closest solar approach on October 29, 2025, passing at a distance of roughly 36 astronomical units, and around October 3rd, as it swept close enough to Mars, NASA and the European Space Agency scrambled to coordinate an improvised observation attempt discussing weather orbiters already stationed at the Red Planet, including ESA's Mars Express and its ExoMars Trace gas orbiter, built for mapping Martian terrain rather than chasing a fast-moving interstellar comet, could be repointed in time to catch a detection from a vantage point no Earth-based telescope could match. It was a genuine technical challenge, attempted on a compressed timeline measured in days, not a guaranteed success, requiring mission planners to weigh the value of a speculative, short-notice observation against every other scheduled use of instruments that normally spend their time mapping dust storms and searching for methane in the Martian atmosphere, and it captured something true about the entire year-long campaign. Humanity didn't have a purpose-built comet-chasing fleet standing by for this exact event. It had a scattered set of spacecraft and instruments built for entirely different jobs, repurposed and coordinated across multiple space agencies on short notice, for an object that gave almost no advance warning and would never pass this way again. As 3IATLAS moved outward from the Sun, freshly warmed and more active than at any earlier point in the campaign, Webb's team secured emergency time to interrupt the telescope's planned schedule and turn its mid-infrared instrument, known as MIRI, toward the comet across 2 sessions, on December 15th and 16th, and again on December 27th. Unlike NIRSpec's single averaged spectrum, MIRI's data could be built into an actual false color image, showing the spatial distribution of specific molecules glowing around the nucleus, processed by researchers M. Belyakov at Caltech and I. Wong at the Space Telescope Science Institute. NASA released it as the first mid-infrared chemical fingerprint ever captured from an interstellar object, and buried inside it was a detection nobody had confirmed on any interstellar visitor before: methane gas. Methane sublimates from ice at far colder temperatures than water does, meaning it should normally boil away and vanish well before a comet gets anywhere near the Sun. Its delayed appearance here, only becoming clearly detectable after the comet had already rounded the Sun and warmed further, suggested it had been buried deep inside the nucleus, shielded from solar heating during the approach, only reaching the surface once warmth had worked its way into progressively deeper, older layers of ice that had likely sat untouched since the object's formation, frozen solid for longer than the Sun itself has existed. A separate NASA instrument, the Sphere-X Observatory, had observed the comet a few weeks before Webb's MIRI session and found its water production rate had jumped roughly 40-fold compared to readings taken before perihelion, additional evidence that solar heating was steadily penetrating further into the nucleus's interior as the weeks passed, gradually exposing older, more deeply buried ice with each stage of the comet's outward journey. A trend that itself argued strongly for a natural, gradually thawing comet rather than any kind of engineered or artificially controlled process. Belyakov noted at the time that Webb's had one further observation of 3IATLAS scheduled for spring 2026, though tracking the comet was already growing more difficult as it faded further from both the Sun and Earth, a fading that would only accelerate in the months that followed as the comet's distance continued to grow and its reflected sunlight continued to dim toward the edge of what even Webb's sensitive instruments could reliably detect. Which brings the story to the finding NASA formally confirmed in June 2026, the one that actually earns the word incredible without any exaggeration required. Cordner's team went back to the NIR spec data gathered as 3IATLAS retreated from the Sun and measured something more subtle and more revealing than simple molecular identification: isotope ratios. Specifically, how much deuterium, a heavier form of hydrogen carrying an extra neutron, sometimes called heavy hydrogen, was locked into the comet's water and organic molecules relative to ordinary hydrogen. The result was, in Cordner's own words, a genuine surprise, one that took the team several additional weeks of cross-checking against instrument calibration data before they felt confident enough in the measurement to submit it for formal peer review. 3IATLAS showed roughly 30 times more deuterium than is typically found in comets native to our solar system, a ratio so far outside the normal range that it functions almost like a birth certificate. Deuterium ratios matter to astrochemists because they're a direct record of temperature. The colder and more distant from a young star that ice originally froze, the more deuterium tends to get locked into it, and that ratio survives essentially unchanged for billions of years afterward, no matter how far the object later travels, preserved like a fossil regardless of how much of the surrounding material has since sublimated away, a durability that makes it one of the most trustworthy tracers available anywhere in observational astrochemistry. A reading this extreme points toward an origin in an extraordinarily cold, extraordinarily remote region of whatever protoplanetary disk 3I-ATLAS originally condensed from, almost certainly colder and farther out than anywhere our own solar system's comets ever formed, a region so far from its parent star that sunlight there, if that star even resembled our own, would have arrived as little more than a faint glow against an otherwise dark sky. Cordner described the finding as a genuinely rare opportunity, a direct sample of material from a distant, ancient part of the galaxy, very likely older than the sun and the solar system themselves, offering both a window into that distant place and time and a way to measure just how unusual, or how ordinary, our own solar system's formation might actually be. By comparison, a question astronomers had previously only been able to approach indirectly, through modeling and inference rather than a direct physical measurement of foreign material. It's worth explaining why astrochemists care about deuterium so specifically, beyond just pinning down where and when an object formed, because the same measurement connects directly to one of the biggest open questions in planetary science. Where did the water and organic material that eventually became Earth's oceans, and ultimately the chemistry of life, actually come from? Comets and other icy bodies are widely suspected to have delivered a meaningful fraction of Earth's water and organic molecules during the earliest, most chaotic period of solar system history, when collisions between forming planets and leftover debris were common, a period sometimes called the era of heavy bombardment. Measuring deuterium ratios in solar system comets has been one of the main tools researchers use to test that idea, by comparing cometary deuterium levels against the deuterium signature actually found in Earth's oceans today, looking for a close enough match to support the delivery hypothesis, an approach that has produced mixed and still debated results, even using solar system comets alone. 3I-ATLAS's deuterium reading, being so far outside anything in that solar system comparison set, is itself informative, precisely because it establishes a genuinely independent external data point, proof that other star systems can produce ice with a completely different isotopic fingerprint than our own, which helps astronomers calibrate just how much variation exists across the galaxy in the raw ingredients available for planet formation, and by extension, for the kind of chemistry that eventually makes life possible somewhere, whether here or around some other star entirely. It's worth sitting with what that means once you stack it against everything else Webb had already found. A coma dominated by carbon dioxide instead of water. Methane buried deep enough to stay frozen for months past perihelion. A deuterium signature 30 times higher than anything cataloged among solar system comets. Around the same period as Webb's own observations, a separate team led by researcher Josep Trigo Rodriguez analyzed the comet's surface composition using ground-based data and reported something else unexpected, though again thoroughly natural. 3I-ATLAS appeared to share compositional traits with dwarf planets and other icy bodies orbiting far beyond Neptune in our own solar system, showing signs consistent with cryovolcanism, essentially cold ice-driven eruptions, rather than the molten rock volcanism familiar from Earth or Mars. Trigo Rodriguez described the team's own surprise at finding that material formed around a completely different, remote star could resemble the makeup of bodies formed at the farthest, coldest edge of our own solar system, a resemblance that, if it holds up under further analysis, suggests certain basic chemical processes in cold, distant regions of forming planetary systems may play out in broadly similar ways across very different stars, hinting at a kind of shared chemistry stretching across the galaxy rather than a set of rules unique to our own solar neighborhood, a possibility with implications well beyond this single comet. None of these findings, individually or together, prove 3I-ATLAS is anything other than a comet, and the overwhelming consensus among the scientists who actually ran the numbers, Lintott, Meach, Lawler, Cordner, and the wider teams behind Hubble, Webb, and Gemini alike, is that it's exactly what it looks like, a natural comet, just one built from raw material, unlike anything native to our neighborhood. But taken together, that chemistry is its own kind of message, not encoded in deliberate signals or engineered structures, but written directly into the object's molecular structure, a genuine sample of what building blocks look like around a star that isn't the sun. There's a reason NASA was willing to interrupt Webb's tightly booked observing schedule twice for this one object, competing against years of pre-approved research proposals from astronomers across every subfield imaginable. And it has nothing to do with aliens. Every planet, asteroid, and comet native to our own solar system formed from the same original cloud of gas and dust roughly 4.5 billion years ago. Nearly everything humanity has ever examined up close, moon rocks, Martian soil, comet material physically returned by spacecraft, comes from that same original batch of ingredients, shaped by the same star, the same disk of leftover debris, the same few hundred million years of chaotic early history. 3IATLAS doesn't share any of that. It's a genuine physical sample of another star system's formation history, delivered to our doorstep on a schedule nobody controls and nobody can repeat. Astronomers don't get to choose when an interstellar object shows up. They don't get to choose what it turns out to be made of. And once it's gone, there's no follow-up mission, no return visit, no second chance to look closer, no matter how many additional questions a given result raises. That's the actual justification behind every emergency allocation of telescope time across this entire campaign, weighed and approved by review committees who understood exactly what they were trading away in order to seize a window that would never reopen. And it's a far better reason than any headline needs to invent. By the time this reaches you, 3IATLAS has already passed beyond Jupiter's orbit, fading fast and growing harder to track by the week, on a hyperbolic path that guarantees it is never coming back. Everything scientists know about it, they had to learn inside a single, unrepeatable year, coordinating Hubble, 2 separate Webb instruments, NASA's SphereX observatory, the TESS satellite, and ground-based telescopes across multiple continents, essentially improvising a real-time cross-agency observation campaign for an object that gave almost no advance warning and will offer no second chance. Every one of those instruments had to be scheduled, calibrated, and pointed by teams who, in most cases, had never planned to study this particular target at all until it suddenly appeared and forced its way to the top of the priority list. And this likely isn't the last time astronomers will have to move that fast. Before Oumuamua, Borisov, and 3IATLAS, humanity had never confirmed a single interstellar object passing through the solar system, simply because existing survey telescopes weren't sensitive enough or fast enough to reliably catch something that faint moving that quickly through the outer solar system. That's changing, and changing quickly. The newly operational Vera C. Rubin Observatory in Chile, built to scan the entire sky every few nights with far greater sensitivity than the survey that first caught 3IATLAS, is expected by many researchers to turn up a new interstellar visitor roughly once a year, once it reaches full operating cadence, and possibly more than one in a good year. A dramatic jump from the roughly 1 per decade detection rate humanity has managed until now. Some scientists studying 3IATLAS's own trajectory have estimated that objects of similar size may be passing through our cosmic neighborhood more often than anyone previously assumed, simply too faint for older instruments to catch, sitting undetected within a few times the Earth-Sun distance at any given moment, an entire hidden population that Rubin's far deeper sky surveys are specifically designed to finally start revealing. The next one may not arrive with as much advance warning as 3IATLAS's unusually large size and brightness gave scientists this time, or it might arrive with considerably more, handing researchers an even richer chemical portrait before it, too, disappears back into the dark it came from. Either way, the coordination playbook that NASA, ESA, and observatories on multiple continents built under real-time pressure this past year, deciding within days which instruments to repoint, which observing schedules to interrupt, and which teams to mobilize, now exists for the next one, which means the response the next time will likely be faster, better organized, and even more thorough than it was for 3IATLAS. So when NASA says it confirms something incredible about 3IATLAS, this is what actually earned that word. Verified against a peer-reviewed publication anyone can go read for themselves rather than take it on faith from a thumbnail. Not a spacecraft, not a signal, not a threat, but a comet carrying isotope ratios that place its birth in a colder, more distant, more ancient corner of the galaxy than anything previously measured up close, a genuine relic from before our own solar system existed, chemically fingerprinted for the first time in human history by the most advanced telescope ever built, and gone again within a matter of months. Along the way, the object survived a serious public scientific argument about whether it might be something built rather than something grown, an argument that named scientists on every side, conducted openly under their own credentials. In interviews and preprints anyone could read in real time, and that landed, by every independent test anyone actually ran, on the side of a comet. Unusual, ancient, chemically distinct, but a comet. No embellishment required, and honestly, none would have improved it. The real find, an ancient piece of another star system passing silently through our own before vanishing forever, carrying chemistry that connects directly to open questions about how water and organic materials spread across the galaxy in the first place, was always going to be the better story than any invented one could have been.